The universe should be a chaotic, crumpled mess. Instead, it is breathtakingly smooth and flat. This serene perfection is the central puzzle of modern cosmology, a deep mystery the standard Big Bang story fails to explain. Our leading solution is a concept called cosmic inflation, a staggering burst of expansion in the first sliver of a second that reshaped everything. By the end, you will understand not only how this idea saved cosmology, but also why it leaves many experts deeply unsettled. We will explore how a theory that solved our greatest puzzles may have opened a door to even stranger and potentially untestable realities. What does it mean when our best explanation for the cosmos creates more questions than it answers? To understand the gravity of this puzzle, we must first look at the oldest light in the universe. This is the cosmic microwave background, a faint afterglow that fills the entire sky. It is a snapshot of the cosmos when it was only 380,000 years old, a baby picture of incredible clarity, and this picture reveals something profoundly strange. No matter which direction you point a telescope, the temperature of this ancient light is almost exactly the same. The differences are minuscule, mere fractions of a degree. This extreme uniformity is the horizon problem. Think of it this way. In the standard Big Bang model, nothing can travel faster than light. For two regions of space to have the same temperature, they must have exchanged energy. They must have been in contact to reach this thermal equilibrium. But when we trace the history of the universe backwards, we find that regions on opposite sides of the sky today were, in that early era, separated by a vast distance. So vast, in fact, that light simply did not have enough time to travel from one to the other. They were beyond each other's cosmic horizon, forever out of touch. It is as if you walked into a vast concert hall and found that every single person, from the front row to the very back, was humming the same note in perfect pitch, yet none of them had ever met or communicated. This apparent coordination across impossible distances seems to violate a fundamental rule of physics. It suggests these distant parts of the universe were once intimately connected, a possibility the original Big Bang story cannot accommodate. This was the first major crack in the model, a clear sign that something crucial was missing from our story of the beginning. But the horizon problem was not the only ghost in the machine. A second, even more profound mystery was hiding in the geometry of the cosmos itself. This is known as the Flatness Problem. To understand it, we need to think about the shape of space on the grandest scale. General relativity tells us that the fabric of the universe can have one of three possible geometries. It can be positively curved like the surface of a sphere, where parallel lines eventually meet. It can be negatively curved like a saddle where parallel lines diverge, or it can be perfectly flat like a sheet of paper where the rules of Euclidean geometry we learned in school hold true. Which one we live in depends on a single critical number, the density of the universe. If the average density of matter and energy is exactly at a specific value called the critical density, the universe is flat. If it is higher, space curves back on itself. If it is lower, space curves outward in an open, infinite saddle. For decades, cosmologists measured and debated, trying to weigh the cosmos. And when the results from satellites like WMAP and Planck came in, they were astonishing. The observed density of the universe is not just close to the critical density, it is indistinguishable from it. The universe, as far as we can measure, is perfectly flat. Now, on its face, that sounds like a simple fact, but within the standard Big Bang model, it is a profound puzzle of unnatural fine-tuning. Think of it like balancing a pencil perfectly on its tip. In theory, it is possible, but the slightest breath of air, the tiniest vibration, will knock it over. The pencil wants to fall. In the expanding universe of the Standard Model, a perfectly flat geometry is just as unstable. Any tiny deviation from that exact critical density in the early universe would have been magnified exponentially over billions of years of expansion. If the density was even a fraction of a percent too high at the beginning, the universe would have collapsed back on itself in a big crunch long before stars could form. If it was a fraction of a percent too low, matter would have spread out so rapidly that galaxies could never have pulled themselves together. For our universe to be as flat as we see it today, its initial conditions, some 14 billion years ago, had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. That is a 1 followed by 60 zeros. It is a number so absurdly precise it defies comprehension. It would be like guessing the exact position of a single, specific atom in the entire observable universe on your first try. This level of precision feels less like a natural outcome and more like a cosmic cheat code, a parameter dialed in with impossible care. The flatness problem suggested the universe we see was not just unlikely, it was preposterously, inexplicably special. And for science, such extreme fine-tuning is not an answer. It is a glaring signal that our model is incomplete, that a deeper mechanism must have been at work to sculpt the cosmos into this delicate, stable state we call home. Yet another ghost haunted the predictions of the early cosmos, one born from the marriage of particle physics and cosmology. This is the Monopole Problem, and it concerns things that should be everywhere but are nowhere to be found. To understand it, we have to venture into the realm of grand unified theories. These are ambitious frameworks in physics that attempt to describe all fundamental forces, except gravity, as different manifestations of a single primordial force. In the unimaginable heat of the very first moments after the Big Bang, according to these theories, the electromagnetic force, the weak nuclear force, and the strong nuclear force were all unified, one and the same. But as the universe expanded and cooled, it underwent a series of dramatic phase transitions. Think of it like water freezing into ice. As liquid water cools, it eventually must choose a crystalline structure. Different patches of water might freeze with their crystals oriented in different directions. Where these differently oriented ice crystals meet, you get a flaw in the structure, a crack or a boundary. In the early universe, as it cooled through the temperature where the unified force split, different regions of space could have chosen different orientations for the new, separate forces. And where these cosmic domains met, topological defects would have formed. The most famous of these predicted relics is the magnetic monopole. Unlike every magnet we have ever seen, which always has both a north and a south pole, a magnetic monopole would be a particle with only one magnetic charge, just a north or just a south. According to grand unified theories, these particles should have been produced in staggering abundance during that early phase transition, as numerous as protons in the universe. They would be incredibly massive, stable, and virtually indestructible. They should still be here today, a fossil population from the first fraction of a second. And that is the problem. Despite decades of sensitive searches, from deep underground laboratories to scans of ancient minerals, not a single, definitive magnetic monopole has ever been observed. The universe appears to be completely devoid of these exotic relics that our best particle physics insists must exist. This posed a severe contradiction. Either our theories of particle physics were fundamentally wrong about the early universe, or something happened to sweep these monopoles clean out of our observable reality. The monopole problem, alongside the horizon and flatness puzzles, formed a triad of crises. Together, they painted a picture of a standard Big Bang model that was not just incomplete, but actively at odds with the serene, flat, and monopole-free cosmos we actually inhabit. A radical new idea was needed, one that could erase these ghosts from our cosmic story in a single, breathtaking stroke. The solution arrived in the late 1970s, a radical rewrite of the cosmos's first moments. Physicist Alan Guth, along with others like Andrei Linde, proposed a breathtaking new prologue to our cosmic story. This was not the Big Bang itself, but a precursor event of unimaginable violence and grace called cosmic inflation. The idea is deceptively simple in its premise, yet staggering in its implications. It posits that for a fleeting instant, a minuscule fraction of a second after time began, the universe was seized by a repulsive force of incredible power. This force was not gravity or any of the familiar forces, but a hypothetical energy field that permeated all of space, a scalar field physicists call the Inflaton. Picture this field like a vast cosmic landscape of energy. In its highest state, it possessed a peculiar property, a sort of negative pressure, and this negative pressure acted like a form of anti-gravity, causing space itself to expand not just rapidly, but exponentially. The numbers defy all intuition. In perhaps as little as 10 to the power of -32 seconds, a duration so brief it has no analogy in human experience, the universe increased in size by a factor of at least 10 to the power of 26. Let us try to grasp that scale. Start with a volume of space smaller than a single proton, a quantum speck. Now, in that blink of an instant, inflation stretches it to a size larger than our entire observable universe today. Every point in that primordial speck is hurled away from every other point at speeds far exceeding the velocity of light. This is not a violation of relativity, for it is space itself that is stretching, carrying matter and energy along for the ride. This single, elegant mechanism does not just tweak the old story, it completely recontextualizes it. That smooth, flat, monopole-free cosmos we inhabit was not the starting condition. It was the breathtaking result. That exponential expansion is the key to the first great mystery. It explains the eerie uniformity of the cosmic microwave background with an elegant, almost inevitable logic. Remember the horizon problem, the puzzle of how regions of space that were never in light-speed contact could share the same temperature. Inflation dissolves this paradox by completely rewriting the starting conditions. Before inflation began, the entire seed of our observable universe was contained within a region of space unimaginably smaller than a single atom. Crucially, this microscopic patch was small enough for light to cross it many, many times over. Every part of it was in direct, intimate contact with every other part. Heat and energy could flow freely, smoothing out any wrinkles, erasing any temperature differences. This tiny volume was in perfect thermal equilibrium, a single, uniform droplet of primordial energy. Then, inflation was triggered. That repulsive force seized this uniform droplet and stretched it exponentially, inflating it to a size larger than everything we can see today. The entire observable cosmos, with all its galaxies and vast voids, is just an inflated fragment of that one, initially connected speck. The reason the temperature is the same in opposite directions of the sky is not a bizarre coincidence, it is a direct inheritance. Those two distant points were once neighbors, practically on top of each other, inside that pre-inflationary patch. The superluminal stretching of space simply pulled them apart to their current, seemingly disconnected positions. It is as if you took a perfectly mixed drop of ink, placed it on a small, unstretched rubber sheet, and then pulled the sheet in all directions until it became the size of a football field. The ink would be spread thin, but it would still be the same uniform color everywhere because it originated from a single, homogeneous source. Inflation tells us the cosmic microwave background is not a mystery of coordination across impossible distances, but a relic of a time when those distances did not exist. The horizon problem vanishes, replaced by a simple, powerful story of causal connections stretched to a cosmic scale. But this dramatic stretching does far more than just connect distant points. It also holds the key to the second great mystery, the puzzle of cosmic flatness. Recall the dilemma that the universe's geometry had to be fine-tuned to an impossible precision from the very start to end up flat today. Inflation rewrites this entire narrative by changing the starting point of the story itself. Think of the universe's geometry not as a fixed trait, but as a shape imprinted on the fabric of space. Before inflation, our entire observable cosmos was an insignificantly tiny speck. Now, consider the geometry of that speck. It could have possessed any curvature, any shape at all on that microscopic scale. It might have been wildly crumpled, twisted, or bent, but then inflation begins stretching that speck by a factor of trillions upon trillions. This is where the analogy of the balloon becomes so powerful. Take a small, wrinkled balloon, perhaps one that has been crumpled in a pocket. Its surface is full of ridges, valleys, and sharp curves. Now begin to inflate it. As the balloon expands, those local wrinkles are stretched smooth. More importantly, if you were a tiny ant living on the surface of that balloon, your entire world would begin to appear flatter and flatter as it grew. From your limited, local perspective, the curvature of the balloon becomes undetectable. The ground beneath your feet seems perfectly flat, even though the balloon as a whole is still a sphere. Inflation does precisely this to the universe, but on a scale so vast it boggles the mind. That exponential expansion smooths out any primordial wrinkles in spacetime itself. More profoundly, it drives the overall geometry toward perfect flatness, regardless of what it was like in the beginning. The mathematics is clear. Any initial curvature, whether positive or negative, is diluted away by that incredible stretching. By the time inflation ends, the observable universe is left so vast that its geometry, from our local viewpoint, is indistinguishable from perfectly flat. The critical density is no longer a magical number that had to be dialed in with 60 decimal places of precision. It becomes the natural, almost inevitable outcome of the inflationary process. The universe is flat for the same reason the ocean appears flat to a sailor on a calm day, not because it was created that way, but because the scale of the curvature is so grand it lies beyond the horizon of our perception. Inflation transforms flatness from an inexplicable initial condition into a predictable consequence, a signature left behind by the violent expansion of space itself. This same process of exponential stretching holds the answer to the final ghost in the machine, the missing magnetic monopoles. Remember, grand unified theories predicted these exotic particles should have been forged in incredible abundance during the universe's first moments, relics of a cosmic phase transition. Their complete absence from our searches was a glaring contradiction. Inflation resolves this by acting as the ultimate cosmic eraser. Imagine that monopoles were indeed produced, scattered densely throughout that primordial, microscopic speck of space. They would have been as common as grains of sand on a beach, but then the inflationary epoch begins. Space itself undergoes that staggering expansion, stretching by a factor of trillions upon trillions. The density of everything in that space, including any monopoles, is catastrophically diluted. Picture sprinkling a single pinch of salt into a thimble of water, then pouring that thimble into the entire Pacific Ocean. The salt is still there in a technical sense, but its concentration becomes so vanishingly small that finding a single grain becomes practically impossible. Inflation does exactly this, but on a cosmic scale. It stretches the original volume containing any monopoles so enormously that their density drops to effectively zero. Our entire observable universe, as vast as it is, likely inflated from a region so small that it simply did not contain a single one of these relics. Their absence is no longer a puzzle, it is the expected outcome. Inflation sweeps the cosmic stage clean, leaving behind a smooth, flat, and monopole-free expanse, ready for the familiar story of the hot Big Bang to begin. With these three profound puzzles elegantly solved, cosmic inflation seemed nothing short of a miracle cure. It provided a single, powerful mechanism that explained the universe's large-scale structure, its geometry, and the absence of certain exotic particles. For a time, it felt like cosmology had found its unifying theory, a prologue so perfect it answered every major question. But this very success would soon give rise to a deeper, more troubling unease. For in solving the old mysteries, inflation may have opened the door to realities far stranger and potentially forever beyond our reach. Yet the true brilliance of inflation lies not just in the problems it erases, but in the universe it creates. Beyond solving the old puzzles, the theory delivered a breathtaking and unexpected gift, the origin of all structure in the cosmos. It tells us where galaxies, stars, and planets ultimately come from, and it did so with a prediction of astonishing precision. This story begins not with grand forces, but with the ghostly whispers of the quantum world. Even in the vacuum of empty space at the tiniest scales, there is a fundamental jitter. Quantum mechanics tells us that fields, like the Inflaton Field driving the expansion, are never perfectly still. They experience constant, tiny fluctuations, virtual particles popping in and out of existence, a seething foam of energy at the quantum level. Normally, these fluctuations are fleeting and microscopic, invisible to the larger world. But inflation changes everything. As space expands at an exponential rate, these infinitesimal quantum ripples in the Inflaton Field get caught in the stretch. A tiny difference in energy here versus there, born from pure quantum chance, is suddenly magnified to a cosmic scale. Imagine the surface of a perfectly calm pond at the quantum scale, with subatomic ripples dancing across it. Now, in an instant, the pond expands to the size of an ocean. Those once tiny ripples are now frozen into vast, gentle waves spanning the entire seascape. This is precisely what inflation does. It takes the random, microscopic jitters of a quantum field and imprints them, stretched to enormous sizes, onto the fabric of spacetime itself. These imprints are minute variations in the density of the universe, regions that are ever so slightly denser or less dense than the average. They are the seeds of everything to come. When inflation ends and the universe transitions into the familiar hot Big Bang, these frozen density ripples are all that remain of that primordial quantum storm. They are not structures yet, merely subtle patterns in the otherwise smooth soup of particles and radiation. But gravity sees them. Gravity is an amplifier of difference. A region with just a tiny bit more mass exerts a slightly stronger gravitational pull, attracting more matter from its surroundings. Over hundreds of millions of years, these subtle overdensities grow, pulling in gas, dark matter, and more, slowly collapsing under their own weight. The gentle waves in the cosmic ocean become the peaks and troughs where galaxies will cluster and vast voids will form. Every great wall of galaxies, every spinning spiral, every planet orbiting a star, can trace its lineage back to those quantum whispers stretched across the sky during the first fraction of a second. This was not just a neat idea, it was a specific, testable prediction. Inflation predicted that these primordial density variations should have a particular character, a specific pattern of strength across different size scales, known as a nearly scale invariant spectrum. And then we looked. The cosmic microwave background, that baby picture of the universe, is not perfectly smooth. It contains faint, mottled patterns of temperature differences, those famous anisotropies. These temperature spots directly map onto those early density ripples, hotter spots where the plasma was slightly denser, cooler spots where it was thinner. When satellites like COBE, WMAP, and Planck mapped this ancient light with incredible precision, they found the pattern. The distribution of hot and cold spots, their sizes and strengths, matched the predictions of inflationary cosmology with stunning, almost uncanny accuracy. It was a monumental confirmation. The theory had not only explained the smoothness and flatness of the universe, it had also told us where the lumps came from. In a single framework, inflation accounted for both the breathtaking uniformity of the cosmos and the rich, intricate structure within it. This predictive triumph cemented inflation's place as the dominant paradigm, the story we tell about the beginning. But within this very success, a subtle unease began to grow. For if the seeds of all structure are born from quantum chance, what does that say about our own cosmic neighborhood, and indeed about the entire nature of reality beyond our horizon? The explanatory power of this idea is difficult to overstate. Cosmic inflation transformed cosmology from a field wrestling with paradoxes into one with a coherent, predictive narrative for the universe's first moments. It did not merely patch the holes in the old Big Bang model, it rebuilt the foundation. Three profound mysteries, the Horizon Problem, the Flatness Problem, and the Monopole Problem, were no longer seen as inexplicable flaws in our cosmic starting conditions. Instead, they became natural, even inevitable, predictions of a single, elegant mechanism, a period of exponential expansion. The eerie smoothness, the precise flatness, and the absence of exotic relics were all signatures left behind by that staggering stretch of spacetime. Furthermore, the theory gifted us with a profound bonus, a mechanism for the origin of all structure. It connected the ghostly realm of quantum fluctuations to the majestic architecture of galaxies, offering a specific prediction that our most powerful telescopes have spectacularly confirmed. This dual achievement, solving old puzzles while predicting new observations, cemented inflation's status as the dominant paradigm in modern cosmology. For decades, it has stood as our best story of the beginning, a narrative of breathtaking scope and compelling internal logic. Yet, within this very triumph, a quiet but persistent question began to form among physicists. If a theory becomes too powerful, too flexible in its explanations, does it risk explaining everything and therefore nothing at all? But this remarkable success comes with a hidden cost. To understand the first major trouble with inflation, we must look under the hood at the very engine that drives it. The Inflaton Field is not something we have ever detected. It is a hypothetical construct, a placeholder in our equations for whatever unknown physics dominated that first instant. We do not know what it is made of, how it interacts with other forces, or even if it is a single field or a complex symphony of them. Its entire existence is inferred from the cosmic effects we believe it must have produced. This means the beautiful story of inflation rests upon foundations we cannot yet see. The field is often described using the metaphor of an energy landscape. Picture a vast, rolling countryside of hills and valleys. The height of the land at any point represents the energy density of the Inflaton Field. In this picture, inflation begins when the field is perched high up on a very flat plateau in this landscape. That plateau represents a state of high energy with that peculiar negative pressure. While the field sits there, it drives the exponential expansion. For inflation to end and transition into the hot Big Bang we know, the field must eventually roll down from this plateau into a lower valley, releasing its pent-up energy as the heat and particles of the newborn universe. This seems straightforward, but the devil is in the details, and those details require an almost magical setup. For the theory to match our exquisitely precise observations, the shape of this hypothetical landscape must be sculpted with unbelievable care. The plateau must be incredibly flat, not just slightly flat, but flat to an extraordinary degree. If the slope is too steep, the Inflaton Field rolls down too quickly, ending inflation before it can solve the horizon and flatness problems. If the plateau has any significant bumps or dips, they would create irregularities in the expansion, imprinting unwanted features on the cosmic microwave background that we simply do not see. Constructing a viable model means tuning the parameters of this unknown field, its mass, its coupling constants, the shape of its potential energy curve, with a precision that can feel unnerving. It must be just right to produce the exact amount of expansion we need and to generate the specific pattern of quantum fluctuations that seed our galaxies. Herein lies the deep irony. Cosmic inflation was celebrated for eliminating the unnatural fine-tuning of the initial conditions in the old Big Bang model. It replaced a universe that had to be born perfectly flat and smooth with a dynamic process that creates those features. Yet, to make that process work, we seem to have simply shifted the fine-tuning. We traded the fine-tuning of the universe's starting state for the fine-tuning of the Inflaton Field's properties. The parameters of this hypothetical entity must be chosen with a delicacy that rivals the very puzzles inflation was meant to solve. This leaves many physicists with a sense of unease. Have we truly explained the specialness of our cosmos, or have we just hidden it one step further back, dressing it up in the language of quantum fields? The Inflaton becomes a deus ex machina, a plot device invoked to save the story, whose own origins and justification remain a profound mystery. This fine-tuning is not the only shadow cast by the inflationary paradigm. The theory's own internal logic seems to lead to a consequence so vast and strange it challenges the very meaning of science itself. To see why, we must follow the mathematics of the Inflaton field to its ultimate conclusion. In many viable models, the process that ends inflation in our region of space is not a global shutdown, but a local event. Picture that energy landscape again, with its high plateau and lower valleys. In our cosmic neighborhood, the Inflaton field rolled down into a valley, releasing its energy to create our hot Big Bang universe. But what about the rest of that vast plateau? According to the equations, the exponential expansion of space is so ferocious that it can outpace the field's roll downhill. While our pocket of the cosmos settled down, the space just beyond our horizon continued to inflate at an exponential rate. And it may do so forever. This is the concept of eternal inflation. Once triggered, inflation becomes a self-perpetuating, unstoppable process in the bulk of reality. Our universe is not the end product of inflation, but a single bubble that formed within an eternally inflating sea. Worse, our bubble is not unique. Quantum fluctuations in the Inflaton field can, in different regions of this eternally stretching background, trigger the formation of other bubbles, other pocket universes. Each one experiences its own roll down the landscape, its own transition to a hot Big Bang, its own set of physical laws determined by which valley its Inflaton field settled into. The result is not a universe but a multiverse, a vast, perhaps infinite ensemble of disconnected cosmic domains, each with its own history, its own particles, and crucially, its own fundamental constants. In some bubbles, the strength of gravity might be stronger, preventing stars from ever forming. In others, the nuclear forces might be too weak to bind protons and neutrons, leaving only a featureless haze of particles. The vast majority of these pocket universes would be sterile, lifeless voids. Only in a rare subset, where the constants are balanced within an extraordinarily narrow window, could complexity, chemistry, and life arise. We find ourselves inevitably in one of those rare, hospitable bubbles. This idea resolves the fine-tuning problem in a radical way. The laws of physics in our universe are not uniquely designed. They are a cosmic accident, a random draw from an infinite lottery. The Inflaton field does not need delicate tuning because every possible value of its parameters is realized somewhere in the limitless multiverse. What feels like miraculous fine-tuning to us is simply a selection effect, an anthropic necessity. We could not observe a universe that did not allow for observers. While this provides a philosophical answer, it comes at a tremendous cost to predictive science. If every possible outcome exists somewhere in the multiverse, then our specific, measurable universe loses its explanatory power. Any observation we make, no matter how unlikely, becomes inevitable in an infinite ensemble. The theory becomes unfalsifiable. we are left with a chilling question. Has our most successful cosmological story led us to a truth that is, by its very nature, beyond the reach of empirical test? This descent into a multiverse is where the triumph of inflation begins to curdle into a deep philosophical crisis for physics. The core issue is one of scientific power, or rather, the loss of it. A successful scientific theory is not just a good story, it is a predictive engine. It tells us what we should expect to see in our experiments and observations. It makes specific, falsifiable claims about reality. If a measurement contradicts those claims, the theory must be revised or discarded. This process of prediction and test is the beating heart of the scientific method. But what happens when a theory predicts not a single, testable outcome, but every possible outcome? This is the profound dilemma posed by the inflationary multiverse. If an infinite ensemble of pocket universes exists, each with different physical constants and laws, then our universe is just one random sample. Any property we observe, from the exact value of the cosmological constant to the mass of the electron, can be explained away not by fundamental law but by chance. We observe these values because in a universe with different values, we would not be here to observe anything. This is known as the anthropic principle, a logical tautology that, while perhaps true, acts as a conversation stopper for science. It replaces the search for a deep, underlying reason with a shrug of cosmic statistics. The theory becomes dangerously flexible, able to accommodate any finding by simply noting that in some bubble of the multiverse, that finding must occur. When a theory can explain everything, it ultimately explains nothing at all. It loses its specificity, its predictive bite, and its power to surprise us. Cosmology, a field built on precise measurement and deduction, risks drifting into the realm of untestable metaphysics, a beautiful narrative that may be true, but one we could never prove or disprove from within our solitary bubble. This elegant shifting of the problem masks a deeper, more fundamental critique. The theory demands its own perfect beginning. For inflation to start at all, the tiny patch of space that would become our universe must have already been in a remarkably special state. It needed to be smooth, flat, and dominated by that Inflaton Field perched on its high-energy plateau. This starting configuration is one of incredibly low entropy, a state of supreme order. In many ways, it is just as finely tuned, just as statistically unlikely, as the perfectly balanced universe the old Big Bang model required. The critic's argument is sharp. Inflation does not explain why the universe began in such an ordered state. It simply assumes that order as its starting pistol. The theory appears to push the mystery of origins one step further back in time, trading one set of special initial conditions for another. We replace a miraculously flat cosmos with a miraculously prepared Inflaton Field. So, does inflation truly provide a more fundamental origin story, or has it merely relocated the cosmic question mark? This is not a minor technicality. It strikes at the heart of the theory's promise to explain our universe's apparent design. If the Inflaton Field itself requires inexplicable fine-tuning to begin its work, then we have not escaped the puzzle of beginnings, we have only given it a new name. The quest for a complete cosmological narrative seems to hit a wall, suggesting that any explanation for our universe's structure may always require us to postulate something even earlier, something even more pristine and unlikely. This leads to a haunting possibility. Perhaps the ultimate origin of everything lies in a realm where our conventional notions of cause, time, and even physical law simply break down. The multiverse does not just challenge our ability to test theories. It confronts us with a mathematical paradox so deep it threatens to unravel the very concept of probability. In a truly infinite ensemble of pocket universes, where every possible event occurs an infinite number of times, how do we calculate what is likely or unlikely? This is known as the measure problem, and it is a technical nightmare hidden within the grand vision of eternal inflation. Probability is the language of prediction. We say a certain outcome is likely if, in a large number of trials, it happens more often than not. But infinity breaks this common sense. Imagine you have a bag containing an infinite number of marbles. Some are blue, some are red. If you ask what the probability is of drawing a blue marble, the answer depends entirely on how you count them. Are there twice as many blue marbles as red? 10 times as many? If both colors are infinite in number, the ratio is undefined without a specific counting procedure, a specific measure. In an eternally inflating multiverse, every conceivable history, every arrangement of particles, every variation of physical constants is realized not just once but an infinite number of times. There are infinite bubbles where the laws of physics allow for stars and planets, and infinite bubbles where they do not. There are infinite bubbles where a planet just like Earth exists, and infinite bubbles where it does not. When everything happens infinitely often, the simple tally of occurrences becomes meaningless. To say we are likely to observe one type of universe over another requires a rulebook for comparing different infinities, a way to cut the endless expanse into comparable chunks. Physicists call this rulebook a measure. The trouble is, there is no single, obvious, God-given measure for an eternally inflating spacetime. Different choices seem equally plausible mathematically, yet they yield wildly different probabilities. One measure might suggest that observers like us are exceedingly rare, a cosmic fluke. Another, equally valid measure might imply we are utterly typical, that almost every observer in the multiverse lives in a universe nearly identical to ours. This is not a minor disagreement. It strikes at the core of using the multiverse to explain anything. If we want to say the measured value of the cosmological constant is probable because most life-friendly bubbles have a value close to ours, we first must choose how to define most. And that choice is arbitrary. Without a unique, well-motivated measure, the multiverse cannot make firm predictions even in principle. It offers a landscape of possibilities, but no reliable map telling us which path we are actually on. The measure problem transforms the grand inflationary multiverse from a potentially testable framework into a realm of profound ambiguity, where the answers we seek dissolve into questions about how to count forever. The most powerful evidence for inflation remains indirect, a story written in the geometry of the cosmos and the pattern of ancient light. We see the breathtaking consequences, but we have never glimpsed the cause. The Inflaton Field, the hypothetical engine of this entire process, has never been directly detected. Its existence is inferred, a brilliant piece of theoretical scaffolding required to hold up the beautiful structure we observe. This places cosmic inflation in a peculiar and frustrating category. It is a theory supported by a wealth of circumstantial evidence so compelling it feels nearly undeniable. Yet it lacks the definitive, smoking gun confirmation that would seal its status as settled physics. Consider a parallel from particle physics. For decades, the Higgs field was a theoretical necessity, the mechanism that explained how other particles acquire mass. Its existence was woven into the very fabric of the Standard Model, but the theory was not considered complete, not truly proven, until the Large Hadron Collider directly detected the Higgs boson, the quantum ripple in that field. That direct detection transformed the Higgs from an elegant idea into an observed component of reality. Inflation finds itself in the pre-collider state. We have the cosmic consequences, the flat universe, the specific pattern of fluctuations, but we have not yet found the particle or the direct signature that shouts, "This was the inflaton." We do not know its energy scale, its specific couplings, or its true nature. This leaves the core mechanism of the theory, however elegant, floating in a realm of persuasive inference rather than direct observation. It is like reconstructing a cataclysmic storm from the precise pattern of debris it left across a continent, yet having no photograph of the storm itself. The reconstruction can be flawless, the explanation perfectly coherent, but the yearning for a direct image, a piece of the storm's own substance, remains. For many physicists, this is the central lingering trouble. A theory can explain everything we see and still feel incomplete until we can touch the machinery that makes it run. The search for that direct evidence, for a unique imprint in the cosmos that could only have been made by inflation's violent birth pangs, is now one of the most urgent quests in all of science. The most promising clue would be a faint tremor in spacetime itself. During that violent burst of exponential expansion, the quantum jitters would not have affected just the Inflaton Field. According to general relativity, the very fabric of spacetime would have been shaken by the process. These quantum fluctuations in gravity would have been stretched to cosmic scales, creating a background hum of primordial gravitational waves rippling through the newborn universe. Unlike the gravitational waves we detect today from colliding black holes, these would be immeasurably older and weaker, a whisper from the first fraction of a second. Their detection would be the closest thing we could get to a direct snapshot of inflation in action, a fingerprint left in the structure of reality. For decades, cosmologists have hunted for this ghostly signal, knowing it could transform our story from a compelling inference into an observed fact. The search has become one of the grandest experiments in the history of science, a quest to hear the echo of creation. This echo would leave a subtle but distinct mark on the oldest light we can see. When the cosmic microwave background radiation was released, those primordial gravitational waves rippling through the universe would have gently tugged on the plasma, imparting a specific kind of swirl to the light's polarization. Polarization is simply the orientation of light's electric field. The CMB light is polarized in patterns that tell a story. Most of the polarization comes from simpler processes, creating patterns known as E-modes. But the twisting force of gravitational waves would generate a different, rarer pattern called B-mode polarization. Think of it like the surface of a pond. If you drop a single pebble, it creates circular ripples that spread outward, an E-mode pattern. But if you stir the water with a spoon, you create a swirling, curling motion, a B-mode pattern. Finding this specific curl in the polarization of the ancient afterglow would be a smoking gun for gravitational waves from the inflationary epoch. It would be a direct imprint of spacetime's quantum shudder, magnified to a cosmic scale, a piece of evidence untouched by the later chaos of galaxies and stars. The signal would be incredibly faint, a whisper nearly drowned out by the cosmic noise of dust in our own galaxy and the subtle distortions from intervening matter. Finding it is like trying to hear a single, specific note played by a violin in the middle of a roaring hurricane. The pursuit of this signal has driven the creation of some of the most sensitive instruments ever built. Telescopes have been placed at the driest, highest, coldest places on Earth, from the Atacama Desert to the South Pole, to peer through the thinnest possible slice of atmosphere. Balloons have carried detectors to the edge of space. Teams with names like Bicep, Keck Array, and Polar Bear have spent years meticulously mapping the polarization of the CMB, filtering out the confounding effects of galactic dust with painstaking care. The journey has been a roller coaster of hope and caution. In 2014, one team announced a thrilling potential detection of these primordial B-modes, a moment that sent waves of excitement through the global physics community. But further analysis, aided by data from the European Space Agency's Planck satellite, revealed that the signal could be entirely explained by interstellar dust within our own Milky Way. It was a sobering lesson in cosmic forensics. The definitive signature of inflation's gravitational waves has not been found. This non-detection is itself a powerful result. It places severe constraints on the simplest, most elegant models of inflation, those that predict a strong, readily detectable wave signal. the universe, it seems, may have inflated in a quieter, more subtle way than we had hoped. The search continues with ever more precise experiments, but each null result gently pushes the theoretical possibilities into a narrower and sometimes more complex corner. The dream of a clean, simple confirmation remains just out of reach, leaving us with a profound question. Is the silence itself a message, telling us our beautiful story of the beginning needs another, deeper rewrite? The silence of those gravitational waves is not a dead end but a crossroads. For some physicists, the persistent troubles with inflation, the fine-tuning, the descent into a multiverse, the lack of a definitive signal, are not minor quibbles but a call to explore entirely different beginnings. A small but dedicated community is asking a radical question. What if the universe never went through an inflationary epoch at all? The search for answers has led to a landscape of alternative cosmologies, each offering a different prologue to our cosmic story, each striving to explain the same serene features of our universe without invoking that brief, violent burst. One profound line of thought challenges the very notion of a singular beginning. These are the bouncing or cyclic cosmologies. In these models, the Big Bang was not the absolute start of time, but a transformative event in an eternal cycle. Picture a universe that undergoes endless epochs of expansion and contraction. In the most well-known versions, like the cyclic model developed by Paul Steinhardt and Neil Turok, our universe exists as a three-dimensional brain floating in a higher dimensional space. These brains could periodically collide, with each collision depositing an enormous amount of energy, triggering what we perceive as a hot, dense Big Bang. The universe then expands and cools, forming galaxies and stars over billions of years, before the expansion eventually reverses in a long, slow contraction, leading to another collision and another bang. This is a cosmos without a true beginning or end, an eternal rhythm of renewal. The appeal is elegant. It naturally addresses the horizon and flatness problems. In each cycle, the universe is stretched and smoothed during the long expansion phase, then reheated and reset during the bounce, wiping the slate clean. The monopole problem vanishes because relics from previous cycles are diluted or transformed in the fiery collision. Most intriguingly, it sidesteps the need for a special, low-entropy starting point by making the universe eternally old, with each cycle inheriting a smoothed state from the one before. Yet this beautiful symmetry comes with immense challenges. The physics of the bounce itself, the moment of transition from contraction to expansion, requires exotic new forces or dimensions to avoid a catastrophic singularity, a point of infinite density where our known laws of physics break down. Making the model match the exquisite details of the cosmic microwave background, particularly the specific pattern of fluctuations we observe, has proven extraordinarily difficult. Another contender emerges from the world of string theory. String gas cosmology proposes that the early universe was a hot, dense tangle of the fundamental strings postulated by string theory. In this view, the universe begins small, but not as a singularity. It is a compact, nine-dimensional space filled with a gas of vibrating strings. As this string gas cools, only three of those spatial dimensions are allowed to expand, while the others remain tightly wound up at a microscopic scale, explaining why we perceive only three dimensions of space. The expansion we see is driven by the thermodynamics of this string gas, not by a repulsive Inflaton Field. Proponents, like Robert Brandenberger and Kamran Vafa, argue that this framework can also produce a nearly scale invariant spectrum of density fluctuations, similar to inflation's prediction, through the quantum vibrations of strings themselves. It offers a potentially more natural connection to a fundamental theory of quantum gravity. However, string gas cosmology remains highly speculative, as it is built upon string theory, which itself lacks direct experimental confirmation. The mathematical complexity is staggering, and turning its conceptual promises into specific, testable predictions that differ from inflations has been a slow and arduous process. Other ideas venture even further. Some models propose that the speed of light was much higher in the early universe, allowing distant regions to communicate and smooth themselves out without superluminal expansion. Others suggest modifications to Einstein's gravity itself in those first moments. Each alternative is a testament to human ingenuity, a different attempt to solve the same cosmic puzzles. But they all share a common burden: the incredible success of the inflationary paradigm. Any new theory must not only explain the smoothness, flatness, and structure of the universe, it must also explain why inflation's specific predictions for the cosmic microwave background, predictions borne out with stunning accuracy, are so precisely right, but for the wrong reasons. This is a formidable hurdle. For now, these alternatives remain intriguing possibilities on the fringe, their mathematical frameworks less developed, their connection to observable data less precise. They represent the healthy skepticism essential to science, a reminder that even our most beautiful and successful stories are not sacred. They are hypotheses waiting to be confirmed, refined, or ultimately replaced by something deeper. This very adaptability, which once made inflation so compelling, has become its greatest philosophical vulnerability. A theory that can explain almost any outcome risks explaining nothing at all. The core idea of a brief, exponential expansion is powerful, but the specific implementation is not set in stone. There is no single, canonical model of inflation. Instead, it is a vast, sprawling framework, a cosmic playground where theorists can construct countless variations. The Inflaton Field's potential energy landscape can be sculpted into an almost infinite array of shapes, different hills, plateaus, and valleys. Each unique shape corresponds to a different model, each making subtly different predictions about the strength of gravitational waves, the exact pattern of density fluctuations, and the duration of the inflationary burst. This flexibility is, in one light, a tremendous strength. It allows the framework to adapt to new data, to incorporate insights from particle physics, and to explore a wide range of possibilities for the universe's first moment. It turns inflation into a versatile language for describing the early cosmos. But this virtue has a dark twin. Critics, including some prominent voices within cosmology itself, argue that this very versatility has rendered inflation nearly unfalsifiable. If a new observation from the cosmic microwave background seems to contradict the predictions of the simplest, most elegant inflationary model, a theorist can simply adjust the shape of the inflaton potential, tweak a parameter, or add another field to the mix. There is almost always a way to modify the model to fit the new data. This ability to accommodate almost any observational result turns the scientific process on its head. A robust theory is supposed to make bold, specific predictions that can be proven wrong. That risk of falsification is what gives a theory its power and credibility. But if a framework can be endlessly adjusted to fit whatever we see, it becomes more of a descriptive paradigm than a predictive theory. It is like having a lock that can be opened by a million different keys. The lock still exists, but its ability to guard a specific truth is gone. Some physicists worry that inflation has crossed this line, becoming a story so flexible that no conceivable observation of our universe could ever disprove its core premise. We could always invent a new inflaton potential to match the evidence. This shifts inflation from the realm of testable science into the domain of metaphysics, a compelling narrative that may always be true in some form, but one we can never definitively pin down. The fear is that we have built a theory of the beginning that is, by design, too resilient to ever fail, and in science, a theory that cannot fail can never truly succeed. This leaves us at a precipice, staring into a profound philosophical abyss. The very features that make cosmic inflation so successful also conspire to make it potentially untestable. We are left with a framework of breathtaking explanatory power, yet one that seems to slip through our fingers whenever we try to grasp it with definitive proof. This is the core dilemma for the physicist. On one hand, the theory elegantly solves our greatest cosmological puzzles and predicted the detailed structure of the cosmic microwave background with uncanny accuracy. It feels like a true description of reality. On the other hand, its logical extensions lead to a multiverse where every possibility is real, rendering specific predictions about our universe meaningless without an unsolvable rulebook for comparing infinities. The theory's own flexibility allows it to morph and adapt to nearly any new observation, making it incredibly difficult to disprove. And after decades of searching, we still lack the direct, smoking gun evidence, like the signature of primordial gravitational waves, that would lock the story into place. This combination creates a perfect storm of uncertainty. How do you falsify an idea that can explain any outcome? If a new telescope finds a surprising pattern in the ancient light, inflation can likely accommodate it with a tweak to the Inflaton Field's potential. If we never detect the telltale swirl of gravitational waves, proponents can point to models where that signal is simply too faint for our instruments. The theory survives, but at what cost to its scientific vitality? A good theory must stand in the arena of evidence, risking everything. But if a theory can never truly be voted out of that arena, has it ceased to be science and become something else, a compelling story we choose to believe? This is the unsettling quiet at the heart of modern cosmology. We have a narrative that works, that feels right, that connects quantum jitters to galactic superclusters. Yet, we must honestly ask, are we building a cathedral of understanding on a foundation that may forever lie beyond the reach of our instruments? The work continues, the searches grow more precise, but the shadow of the question remains, a reminder that our quest to understand the beginning may have led us to the very edge of what is knowable. This situation forces us to confront the very purpose of a scientific explanation. For centuries, the goal has been to find a single, elegant set of laws that uniquely predict the universe we see. We assume reality has a definite structure, and our job is to decode it. But if the inflationary multiverse is correct, that assumption shatters. There is no single, predictable universe. There is only a cosmic lottery, and we hold the winning ticket for life. This does not feel like an explanation in the traditional sense. It feels like a statistical shrug. The question shifts from why our universe has these specific properties to why we find ourselves in a universe that allows us to ask the question. This is a profound philosophical pivot. Some argue it is a necessary step toward a deeper, if more unsettling, truth. Others see it as a retreat, a surrender of science's ambition to explain the world in terms of fundamental necessity. The debate cuts to the core of what we think science is for. Is its ultimate aim to describe a single, objective reality, or to map the vast landscape of all possible realities, even if we can only ever visit one? This tension places cosmology in a uniquely challenging position. It is a science that studies the totality of existence, yet it may be forever trapped inside a single sample. When your subject is everything but your data comes from one particular everything, the rules of the game change dramatically. It raises a haunting possibility. Are we approaching a post-empirical era in fundamental physics? A point where our most promising theories about the origin and totality of reality become, by their very nature, impossible to verify with direct observation. The edge of our observable cosmos is a permanent horizon, and the multiverse, by definition, lies forever beyond it. This creates a profound responsibility for scientists. How do we proceed when the most compelling answers to our biggest questions may be permanently out of reach? One path is to relentlessly push the boundaries of observation, searching for any faint, indirect trace of those other realms in the precise details of our own. Another is to refine the theoretical frameworks, searching for a version of the story that makes sharper, more testable predictions for our cosmic bubble, even if the greater multiverse remains hidden. And a third is to honestly acknowledge the limits of our methods, to distinguish between what is scientifically testable and what remains a compelling but ultimately philosophical speculation. This is not a failure of science but a maturation. It is the recognition that some mysteries of existence might reside in a domain forever beyond our empirical grasp. Yet the very act of mapping that boundary, of understanding what we cannot know and why, is itself a monumental achievement. It teaches us humility about our place in the cosmos, and it clarifies the extraordinary power and the ultimate limits of the human drive to comprehend the beginning of everything. The silence from the cosmos is not a command to stop, but a call to listen more carefully. This unresolved tension between theory and observation is precisely what drives the next great wave of cosmological experiments. Scientists are not idly debating philosophy. They are building ever more sensitive instruments designed to probe the faintest whispers from the universe's first moment. The goal is to move beyond the broad strokes of the inflationary story and test its specific, detailed predictions, searching for the subtle imprints that could finally confirm which version of the tale is true, or if we need a wholly new script. The primary battlefield remains the cosmic microwave background, that ancient afterglow which has already revealed so much. Current telescopes, stationed in the world's highest and driest deserts, have pushed our vision to its limits. The next leap requires an entirely new class of observatory. Projects like the Simons Observatory in Chile's Atacama Desert and the even more ambitious CMB-S4, planned for the South Pole, represent a monumental step forward. These are not single telescopes, but vast arrays of thousands of superconducting detectors, working in unison to map the CMB's polarization with a precision we can barely conceive of today. Their mission is to scour the sky for that elusive B-mode polarization, the swirling pattern that would be the signature of primordial gravitational waves. But they are not simply looking for a signal, they are hunting for a specific pattern within the signal. The exact shape and strength of this B-mode curl would tell us the energy scale at which inflation occurred. It would reveal whether the Inflaton Field rolled gently down a shallow slope or tumbled off a steep cliff, effectively allowing us to weigh the engine of creation. These observatories will also measure the temperature and E-mode polarization fluctuations with such exquisite detail that they could detect minute deviations from the simplest inflationary predictions. A slight unexpected twist in the statistical pattern could point toward more complex models involving multiple fields, or even hint at features in the Inflaton landscape itself, like bumps or dips on that hypothetical plateau. It is forensic science on a cosmic scale, searching for fingerprints in the oldest light in existence. Alongside this relentless gaze into the microwave sky, a parallel quest is unfolding to detect the gravitational waves themselves, not through their effect on light, but directly as ripples in spacetime. While ground-based detectors like LIGO and Virgo listen for the crashes of black holes and neutron stars, a future space-based observatory, like the proposed Laser Interferometer Space Antenna, or LISA, could potentially hear a much older hum. LISA would consist of 3 spacecraft flying in a giant triangle, millions of miles apart, using lasers to measure distances with picometer precision. It is designed to detect low-frequency gravitational waves, including those possibly generated during later stages of cosmic phase transitions, while not directly targeting the inflationary background, which is at a far lower frequency. A confirmed detection of any primordial stochastic background by LISA or similar missions would revolutionize our understanding of the early universe's violence. It would prove that spacetime itself can carry memories from epochs we can never see with light. Furthermore, large-scale galaxy surveys, like those conducted by the Dark Energy Spectroscopic Instrument and the future Euclid and Roman space telescopes, will map the three-dimensional distribution of billions of galaxies. By tracing how cosmic structure clusters over immense scales, they can look for indirect echoes of those initial quantum fluctuations. Any statistical anomaly in the way galaxies are scattered across the cosmos could reflect a peculiarity in the inflationary mechanism that seeded them. Each of these experiments functions like a different instrument in a vast orchestra, each sensitive to a different frequency of the cosmic symphony. The CMB observatories listen for the fundamental tone, the deep bass note from the very beginning. The gravitational wave detectors try to hear the reverberations in the hall of spacetime. The galaxy surveys analyze the complex harmonies that developed over billions of years. Together, they are conducting a grand audit of the inflationary paradigm. They aim to do more than just say yes or no to inflation. They seek to read the fine print. A clear detection of primordial B modes would be a transformative triumph, strongly favoring inflation and pinpointing its energy. A continued, definitive non-detection, however, would be equally revolutionary, forcing us to severely constrain or even abandon the simplest and most popular models, sending theorists back to the drawing board for a new origin story. This is the beautiful, rigorous process of science at its best, a dialogue between bold ideas and even bolder evidence. We are building machines to ask the universe a direct question, and for the first time, we are on the verge of being sensitive enough to hear its answer, no matter how faint the whisper. The ultimate fate of inflation will be decided not just by telescopes, but by the pencil and paper work of theorists. While experiments push observational frontiers, a parallel revolution is unfolding in the realm of pure theory, where physicists are attempting to rebuild the story of the beginning from more solid ground. The goal is ambitious, to either anchor inflation firmly within a deeper framework, like string theory or quantum gravity, or to construct such minimal, elegant versions that they make sharp, unavoidable predictions for our universe. This is the field's attempt to confront its own philosophical troubles head-on. One major thrust seeks to derive inflation as a necessary consequence, rather than an arbitrary add-on. For decades, inflation has felt like a prologue we wrote because we needed it. The dream is to show it emerges inevitably from the mathematics of a more complete theory of everything. String theory, with its extra dimensions and vast landscape of possible vacuum states, has been a primary arena for this search. The hope was that the Inflaton Field might be identified as a specific vibration of a string or a particular geometry of the compactified dimensions. In this view, the inflationary expansion would not be a mysterious event, but the natural settling of the cosmos into a stable state as it cooled from a higher dimensional beginning. Yet this path has proven fraught. String theory's infamous landscape of possibilities, with its 10 to the power of 500 or more distinct vacuum states, seems to amplify the multiverse problem rather than solve it. It provides a potential home for eternal inflation's countless bubbles, but it does not uniquely predict our specific inflationary history. Instead of narrowing the possibilities, it often expands them, leaving theorists to ask if a deeper principle within string theory, perhaps related to quantum entanglement or holography, could select one unique, testable inflationary scenario. This search for a principle is crucial. It is the difference between a theory that describes a near-infinite array of possible universes and one that explains why our universe had to be this way. Another path represents a stark philosophical shift, moving away from the endless flexibility of the inflationary framework. Some theorists are advocating for a return to minimalism. They ask, what is the simplest, most constrained model of inflation we can possibly build? one with the fewest adjustable parameters and the most definitive observational signatures. The idea is to construct models so rigid in their predictions that they stand or fall decisively on a single piece of data, like the precise spectral tilt of the CMB fluctuations or the absolute amplitude of gravitational waves. This is a deliberate attempt to reintroduce falsifiability, to build a version of inflation that cannot easily morph to fit new data. If such a minimal model were ruled out by observation, it would force a major crisis for the entire paradigm, a necessary risk that the current flexible framework often avoids. This work often involves tying the Inflaton Field directly to known or speculated particles in particle physics, like the Higgs boson or a new scalar field predicted by supersymmetry. By connecting the cosmic story to the laboratory story, theorists hope to ground inflation in physics we can, in principle, test with particle colliders or tabletop experiments. Finally, there is a push to look for novel, unexpected consequences of inflation that might leave imprints elsewhere. If the primary CMB signatures remain elusive, could the violent processes at the end of inflation have produced other relics? Some models suggest the creation of ultralight particles that form a fuzzy halo of dark matter, or primordial black holes forged from dense lumps in the Inflaton Field's decay. Others explore whether the transition out of inflation generated a secondary, much weaker background of gravitational waves at higher frequencies, a signal future space-based detectors might one day hear. These are the theoretical long shots, the fingerprints we have not yet thought to look for. The field is in a state of creative tension, actively grappling with the foundations of its most successful story. It is a necessary struggle, a sign of a healthy science confronting its own limits. The theoretical path forward is not about discarding inflation, but about demanding more from it, asking it to be not just a good story, but a necessary one, predicted by a deeper law and yielding clear, testable marks on our reality. This intellectual ferment ensures that, regardless of what the next generation of telescopes reveals, our understanding of the cosmic dawn is poised for a profound evolution. Yet for all its philosophical quandaries, cosmic inflation stands unchallenged as our most powerful story. It remains the only framework that successfully organizes the vast and growing catalog of cosmic data into a coherent, predictive narrative. The evidence for its consequences is etched across the sky in the flat geometry, the specific pattern of ancient light, and the very existence of galactic structures. While its foundations may feel provisional, the explanatory power it provides is not something science can simply walk away from. Think of it as a necessary map for a territory we are still exploring. The map has blank spaces, its legend includes speculative creatures like the Inflaton, and its edges hint at lands we may never reach. But it is the only map we have that consistently guides us from one landmark to the next, predicting what we will find over the next ridge. It organizes our questions, focuses our experiments, and provides a common language for thousands of researchers. Without this paradigm, cosmology would risk dissolving into a collection of disconnected puzzles, with no overarching story to tie the horizon problem to the seeds of galaxies. Inflation provides that story, and for now, nothing else comes close to matching its detailed agreement with observation. This does not mean physicists are satisfied. Quite the opposite. The very act of having such a successful yet troubling framework defines the current frontier. It creates a clear mission to either discover the definitive evidence that anchors inflation in detectable physics, or to be provoked by a stubborn contradiction into imagining a radically different beginning. The paradigm is necessary precisely because it is so testable and so full of unresolved tension. It gives the scientific process a target. Every new telescope, every refined measurement of the cosmic microwave background is a direct interrogation of this idea. The healthy unease surrounding inflation is not a sign of weakness, but a sign of a theory doing its job. it makes strong claims about reality that we are now equipped to investigate. We are in a period of extraordinary potential where our tools are finally becoming sensitive enough to read the fine print of creation. Whether the next decade brings a triumphant detection of primordial gravitational waves or a confounding silence that forces a revolution, the outcome will be a direct result of engaging deeply with this powerful, problematic, and indispensable story of our cosmic dawn. Cosmic inflation remains a monumental achievement of the human intellect. It took three profound mysteries that threatened to unravel our understanding of the cosmos and solve them with a single, elegant stroke. The horizon problem, the puzzling uniformity of the universe, was resolved by a time when everything we see was once intimately connected in a microscopic speck. The flatness problem, the inexplicable geometric perfection, became the natural outcome of space being stretched smooth. The missing monopoles were simply diluted away into cosmic oblivion by that staggering expansion. And in a breathtaking bonus, the theory told us where galaxies come from, predicting that the seeds of all structure were quantum whispers magnified to a cosmic scale, a forecast confirmed with stunning precision by our telescopes. For these reasons, inflation stands as the most successful and comprehensive story we have for the universe's first moments, yet its brilliance is shadowed by persistent, deep troubles. The engine of this entire process, the Inflaton Field, remains a ghost in the equations, a hypothetical entity we have never detected. To make the model work, this field often requires its own kind of exquisite fine-tuning, seemingly replacing one cosmic mystery with another. The logical extension of many inflationary models leads to eternal inflation and a multiverse, a vast ensemble of disconnected universes where every physical law is possible. This idea, while philosophically provocative, risks making our specific universe just a random accident and renders the theory potentially untestable, drifting from empirical science into the realm of metaphysics. The search for a definitive signature like primordial gravitational waves continues, but so far, the cosmos has offered only silence, pushing the simplest models into narrower, more complex corners. So what are we left with? We are left with a magnificent, unfinished chapter. Cosmic inflation is not a final answer, but a powerful, necessary scaffold. It is the best map we have for a territory we are still desperately exploring, a map that has successfully guided us to breathtaking vistas, but whose own legend is written in a language we do not yet fully understand. It solved our greatest puzzles and in doing so, opened a door to questions even more profound about the nature of reality, the limits of knowledge, and whether the ultimate origin of everything lies forever beyond the horizon of our perception. This tension is not a failure, it is the very heartbeat of discovery. It defines the current frontier of cosmology, reminding us that our quest to understand the beginning is a story still being written, one observation, one calculation, one bold idea at a time.